All right, welcome to the Rutgers Foundations of Probability seminar. This week we have the great pleasure of having Haosui Duanmu to talk to us about his very recent work. Well, it's been, in fact, a work that you have been doing for a while, I suppose, on the extended admissible decision procedures and their non-standard Bayes risk. So Kevin, we've known each other for a few years now, and I think that at the time Kevin was still back then a graduate student at the University of Toronto with Dan Roy and Jeff Rosenthal, if I remember correctly. And Kevin right now is a postdoc at Berkeley with Bob Anderson, if my memory is correct. And yeah, this is really exciting work, and I've known this work for quite a few years, and it's a wonderful thing that their paper is finally to appear in the Annals of Statistics soon. So please let's welcome Kevin to tell us about it.
Okay, thank you very much, Robin, for a very nice introduction, and also for your precise memories about my past. So yes, I'm currently a postdoc fellow at Department of Economics at the University of California, Berkeley, working with Bob Anderson. And today I will talk about this work on statistical decision theory. The title of the talk and the title of our paper is on extended admissible decision procedures and their non-standard Bayes risk. So I think, both Dan and I have been circulating this work for a while. So hopefully you will enjoy it today. So I will start my talk by giving a little bit background introduction to statistical decision theory. I guess, many of you are familiar with the setup, but I will still, introduce notations and stuff like that. So a statistical decision problem here consists of the following ingredients. So first of all, a sample space X and a parameter space zeta and an action space A. And the loss function is taken usually to be a jointly measurable function from zeta times A to the non-negative real line. And we use M1X to denote the set of all probability measures on the sample space. And the model is a collection of probability measures on X indexed by the elements from the parameter space zeta. So here we consider randomized decision procedures, which are simply mappings. Usually we denote these mappings by delta from the sample space X to the set of probability measures on the action space. So basically, if we observe something from the sample space, then the randomized decision procedure delta tells us how to choose randomly from the action space. And we'll write delta XA for the this delta X parenthesis A, and we'll use D to denote the set of randomized decision procedures. And as usual in statistical decision theory framework, we use risk to measure the goodness of decision procedures, and the risk of a decision procedure delta at a particular point theta in theta is denoted by R theta delta, and it is computed by this double integral. So the inner integral is the loss with respect to delta, and the outer integral is taking average of the loss with respect to the model at the point theta. So generally we want to pick a decision procedure which has smallest risk as possible, but this is in many cases not achievable. So we have two criteria we have two notions for optimality. So the first notion is the frequentist notion of optimality, which is usually called admissibility. So here we'll give a short and very quick introduction of admissibility. So suppose we have two decision procedures, delta and delta prime, and epsilon being a positive real number, and we say delta is epsilon dominated by delta prime if the risk of delta prime is everywhere less than the risk of delta minus, is everywhere no greater than the risk of delta minus epsilon. and there exists a point theta 0 in theta such that the risk of delta prime is less than the risk of delta minus epsilon. So as we can see from the right graph, we have three decision procedures, delta 0, delta 1, and delta 3. And we say that the risk of delta 0 is everywhere less than risk of delta 1 by some positive amount. So here, delta 1 is epsilon dominated by delta 0 for some positive epsilon. So we say delta is epsilon admissible if it is not epsilon dominated by any delta prime in D. And we say delta is admissible if it is 0 admissible, and the delta is extended admissible if delta is epsilon admissible for all positive epsilon. So among all three notions of admissibility, admissible is the strongest notion, and it implies extended admissible, and which again implies epsilon admissible for all positive epsilon. So okay, so suppose we now look at the left graph where we have two decision procedures, delta 1 and delta 2. As we can see, both, like, neither delta 1 dominates delta 2 or delta 2 dominates delta 1. So from a frequentist perspective, both decision procedures are admissible, and we can't really choose between delta 1 and delta 2. But however, if we have some prior belief that the true parameter theta lies relatively in the left portion of the parameter space, and then in this case, we will choose delta 1 over delta 2 because the risk of delta 1 at this particular point theta is less than the risk of delta 2. So this gives rise to the Bayesian notion of optimality, which is known as Bayes optimality. So here I will provide a definition of Bayes optimality. So given a decision procedure delta in D, a prior is simply a probability measure on the parameter space theta, and the Bayes risk of delta with respect to a prior pi is denoted by r pi delta, and it is the average risk of delta with respect to the prior distribution pi on the parameter space. And we say delta is Bayes optimum if there exists a prior pi such that the Bayes risk of delta at pi is finite, and the Bayes risk of delta at pi is less or equals to Bayes risk of delta prime at pi for all delta prime in D. So the fundamental question of statistical decision theory is regarding the connections between Bayes optimality and frequentist optimality. So probably the most well-known result is by Abraham Ward, which states that if the parameter space is finite, then if a decision procedure is extended admissible, then it is Bayes. Note that the reverse implication is always true, no matter whether theta is finite or not. So actually, if the parameter space is finite, we know that a decision procedure is extended admissible if and only if it is Bayes. So I will give a very quick graphical proof of the complete class theorem, which regards the connections of Bayes and frequentist optimality in this slide. This is just to echo for the later non-standard proof of a more general complete class theorem. So suppose the parameter space is finite, then let's say the parameter space has n points, theta 1, theta 2, up to theta n. So given any decision procedure delta, its risk is characterized by a risk vector, which is r theta 1 delta, r theta 2 delta, up to r theta n delta. And I can form the risk set, which is the collection of all the possible risk vectors. And with some additional, because I'm considering a set of all randomized decision procedures, so the risk set is convex. And also, given a particular decision procedure delta 0, I can form the lower quantum, which are denoted by Q delta 0, which is a collection of all points x in the n-dimensional Euclidean space, such that each coordinate of those points is less or equals to the risk of delta 0 at theta k. So if delta zero is assumed to be admissible or extended admissible, it can be shown that both the lower quantum and the risk set are convex set, and they only intersect at one point, namely the risk factor of delta zero. So by the hyperplane separation theorem, there will be a hyperplane separating them. And furthermore, one can show that the supporting vector of the hyperplane has non-negative coordinates. So after normalization, the supporting vector will witness the Bayes optimality of delta zero. So the proof of this result is very elegant, and it is known probably from the 40s. And there has been a lot of attempt generalizing the result to infinite dimensional, infinite parameter space. So I think I think it is known from the 60s that in order to regain the connection, the equivalence between some notion of Bayes optimality and frequentist optimality, one must relax the notion of Bayes optimum because of Stein's example. In the normal location model, the maximum likelihood estimator is admissible, but it is not Bayes. However, it is a limit of Bayes procedures. So various attempts has been made. So people consider limit of Bayes procedures, generalized Bayes procedures, or finitely additive Bayes procedures. However, most of those works make assumptions on the model, or for example, in the limit of Bayes work, Jim Berger assumed the model have to come from an exponential family, or some regularity conditions which rule out many of the modern nonparametric and semi-parametric decision problems. So here in this talk and in our paper, with the help of non-standard analysis, we will present a very general theorem on the connection between Bayes optimality and admissibility using a new notion of Bayes optimality. So before I proceed, I will give a very rough introduction on the structure of our non-standard result. And this structure not only applies in this paper, this talk, but it also applies in many of my other works on Markov processes, and recently on general equilibrium theorem in economics. So suppose one is interested in some standard infinite mathematical structures with a well-known finite part. So for example, in this problem, this problem is a very good example. We want to understand the connections of Bayes optimality and the frequentist optimality when the parameter space is infinite. However, we do understand their connections when the parameters is finite. So a way to solve this problem is to first push up and consider the analogs problem in the non-standard structure, which I will define later. And within the non-standard structure, there are a particular type of objects which are called hyperfinite objects. So informally speaking, hyperfinite objects or more precisely, hyperfinite sets are infinite sets, but having the same first order logic properties as finite sets. So that means we could sum over, or we could find a biggest element of a hyperfinite set of non-standard reals, for example. Since we understand the finite standard structure with the duality between a hyperfinite object and a finite object, we can usually, without too much difficulty, get a non-standard theorem in the non-standard structure. And because the non-standard structure is usually constructed from the standard infinite structure, so there usually exists a tight connection between the non-standard structure and the standard structure. So sometimes we can push down our nonstandard theorem and obtain a standard theorem for our standard infinite structures that we are originally interested in. So, okay, so now I will give a gentle introduction to non-standard analysis. So non-standard analysis was introduced by Abraham Robinson back in 1960s. And the starting point of non-standard analysis is a construction of the non-standard real line. So here's the rough drawing of the non-standard real line. So it looks very much like a standard real line. But for example, if one has a microscope and if you look at the origin, and then you will see infinitesimals hanging around hanging around zero. For example, here I denotes them by a negative epsilon or positive epsilon. And if you look at some other points, for example, at 10 to the power of 6, then there are also non-standard real numbers which are infinitely close to 10 to the power of 6. For example, 10 to the power of 6 plus epsilon or 10 to the power of 6 minus epsilon. And if you look at the tails of the non-standard real line, you will see infinite numbers. For example, 1 divided epsilon or negative 1 divided by epsilon. A question which I get a lot is people sometimes confuse non-standard real lines confuse the non-standard real line with the extended real line, which can be obtained by a one-point compactification from the standard real line. So the difference is that in the extended real line, although one do includes a point infinite, but this destroys the algebraic structure on the extended real line. That means that this infinite is really a point which are very different from the rest of the standard real points, because those algebraic operations such as summation or multiplication or minus are not really defined for this infinite element. This is not the case for the non-standard real line. In fact, we have the following powerful principle, which is known as the transfer principle. So the transfer principle states that suppose I have a first order logic statement, and if the statement is true in the standard real line, if and only if the non-standard version of the statement is true in the non-standard real line. So I will give you a very simple example of the transfer principle. So for example, we know that for any two real numbers, A and B, A plus B always equals to B plus A. So by the transfer principle, we know that this abelian property also holds for all the non-standard real numbers. Okay, so the second property is called the kappa saturation principle. So here kappa is a cardinal number. So suppose I have a collection of kappa many statements, and if the collection is finitely satisfiable, that means that if I pick any finite subset of the statement and they can be satisfied simultaneously, then the whole collection of the statement can be satisfied simultaneously. So and I think a result from Luxemburger said that given any cardinal kappa, one can always construct a non-standard structure that is kappa saturated. So I think kappa saturation is really the power behind the non-standard analysis to establish existence result in the non-standard structure. And the third point is the existence of infinite and infinitesimal numbers, as I have already told you when I was explaining the graph. So precisely, there exists x in star r such that the absolute value of x is greater than n for every natural number, and the reciprocal 1 over x is an infinitesimal. And its absolute value is greater than 0 but less than 1 over n for all natural numbers n. So for two elements x and y in the non-standard reals, we say they're infinitely close if their difference is if the absolute value of their difference is infinitesimal, and we will write x approximately equals to y. So all all these constructions of non-standard real line can be generalized to topological spaces, or in particular metric spaces with the right notion of infinite and infinitesimal. So now I will introduce a very important concept in non-standard analysis, which is called hyperfinite probability space. So formally speaking, a set A is hyperfinite if and only if there exists an internal bijection between A and 0, 1 up to n-1 for some non-standard natural number n. So here n could be a finite or an infinite natural number. So as I said before, a hyperfinite set is technically an infinite set, but possesses all the first order logic properties of a finite set. Hyperfinite objects are natural objects to connect discrete and continuous mathematics. So a hyperfinite probability space is then simply a triple omega I omega p, where omega is a hyperfinite set. This is a sample space, and I omega is a collection of all hyperfinite subsets of omega, and p is a function from I omega to star 0, 1, such that p empty set equals to 0, p omega equals to 1, and p is hyperfinitely additive. So as one can see, a hyperfinite probability space behaves exactly like a finite probability space. Okay, so as I mentioned before my introduction of hyperfinite probability space, I said that hyperfinite objects are natural objects to connect discrete and continuous mathematics. So here I will give a simple example of how to use hyperfinite probability space to represent standard infinite probability space. So here, suppose we take T, so here we will take T to be the set 1 over n, 2 over n, up to 1 for some infinite natural numbers. So here T is a hyperfinite set. And for every element in T, I will let, for every element omega in T, I will let P omega equals to 1 over n. So this is known as the uniform hyperfinite probability space. And this hyperfinite probability space can be used to represent the Loeb measure of the unit interval on the unit interval 0, 1. Namely, for every Loeb measurable set A, which is subset of 0, 1, its Loeb measure is the same as counting the number of points in T that are infinitely close to some points in A. So this is an imprecise description of how to use Loeb, how to use this hyperfinite probability space to represent the measure of Loeb measure on 0, 1. So more precisely, when we use something called Loeb measures and the standard part inverse. So if any of you are interested in the details, I'm very happy to talk about them after my talk. But probably it's not worth going into details right now. So okay, now I will introduce our new notion of Bayes optimality, which is known as the non-standard Bayes optimality. So given a decision procedure delta in D, where D is the set of all randomized decision procedures, an internal prior, or sometimes I will refer to as a non-standard prior, is a star probability measure on the non-standard extension of theta. And the internal or the non-standard Bayes risk of delta with respect to an internal prior pi is denoted by star r pi star delta, and it is defined by a star integration with respect to the non-standard prior pi or the internal prior pi. And we say delta is non-standard Bayes if there is an internal prior pi such that the internal Bayes risk of star delta, the internal Bayes risk of delta is less than or approximately to the internal Bayes risk of delta prime for any delta prime in D. So here the less than or approximately equals to means that it's either less than or the risk of the internal Bayes risk of delta with respect to pi is infinitely close to the internal Bayes risk of delta prime with respect to pi. So I'll elaborate a little bit here in the regarding this non-standard Bayes optimality. So I have been in contact with Teddy because I know Teddy, Jay, and Mark and Rafael have also have work related to connections between Bayes and the frequentist optimality. So and they consider a finite mixture of decision procedures, if I remember correctly. So here in our setting, we work with purely standard decision procedures, but allow for non-standard priors. So so we work within standard decision theory framework, but allow us with a much larger collection of priors. And I think this is a reason behind this is like the key reason behind the behind our main result, and it is also the reason why our main result does not require any extra conditions. So here's our main result. So our main result says that a decision procedure delta 0 is extended admissible if and only if delta 0 is non-standard Bayes. So note that this result holds under complete generality without any assumptions on the risk functions, on the model, or on the parameter space, or on the action space. This theorem works for any statistical decision problems. So, so as I said before, so now I will give a little bit graphical proof of the of our non-standard of our main result, and one would say that and one should see see that the proof is similar to the proof of the complete class theorem when parameter space theta is finite. So suppose I'm given a arbitrary parameter space theta, and first of all, by saturation, I can always find a hyperfinite set T theta, T1, T2, Tk. Here I denote T theta by this. So T theta will be a subset of star theta, but it contains theta as a subset. And for each decision procedure delta, I will define its n lower quantum, and the n lower quantum is a collection of points, the collection of all points in this hyperfinite dimensional Euclidean space, such that each coordinate of those points xk is less or equals to the corresponding risk coordinate of delta minus 1 over n. So I think in the graph I drew a sequence of n lower quantum for this decision procedure delta 0. And here delta 0 is assumed to be extended admissible, and I can form the non-standard risk set as I did in the when the parameter space is finite. And of course, the risk set here will also be a subset of the hyperfinite dimensional Euclidean space. So by extended admissibility, there exists a hyperplane separating Q star delta 0 n and the risk set for all natural numbers n. And then by saturation again, there will exist a single hyperplane big pi separating the union of all the n lower quantum of star delta 0 and the risk set. And this this hyperplane pi will have a supporting vector, and we can show that the supporting vector has non-negative coordinate everywhere, and the normalization of this supporting vector will witness the non-standard Bayes optimality of star delta 0. Okay, so as a logician and non-standard analyst, I find our main theorem very elegant, and well, it's it's probably the most general theorem one can get regarding the Bayesian and the frequentist regarding the connections between a Bayesian and a frequentist optimality in statistical decision theory. But I also understand that many mathematicians and statisticians are not familiar with nonstandard analysis. And now I will present two purely standard results. That means their statements do not mention any nonstandard analysis, but those results can be derived from our main result. And these two results will also establish how do we connect a non-standard theorem to purely standard results in the standard structure. So as I said before, a hyperfinite probability space can be used to represent standard infinite probability space. It is also true that in many cases, we can construct standard countably additive probability space from hyperfinite probability space. So in particular, suppose theta is a Hausdorff space endowed with Borel sigma algebra B theta, and let pi be a non-standard probability measure on star theta. And we can always construct the following two objects. First of all, we can always construct a countably additive measure, pi subscript p. We usually call pi subscript p pushdown on the standard measure space theta b theta. And if theta is compact, then the pushdown of pi is a probability measure. And I can always construct a finitely additive probability measure, pi superscript p on theta b theta. So pi superscript p, so we usually call pi superscript p internal pushdown. So as I said, the construction of these two standard elements, especially the first one, requires knowledge from a Loeb measure theory and standard part inverse, and I won't go into details of those constructions, and willing to explain afterwards if people are interested. But I will present in the following example just to give you guys a rough idea of how these constructions will look like. So here, suppose I will take n to be an infinite natural number, and I will let pi be an internal probability measure or a non-standard probability measure concentrating on 1 over n. So that means that pi 1 over n equals to 1. So we can, here the pushdown pi p is simply the degenerate measure on the single point 0. And the internal pushdown pi superscript p is a finitely additive measure such that pi p, the open interval 0, 1 over n equals to 1 for every natural number n. So with some additional assumptions on the risk functions or on the parameter space, there exists close connections between a non-standard pi, its pushdown, and its internal pushdown. So we'll summarize our findings in the following two theorems. So the first theorem says that if the parameter space is compact and Hausdorff and risk functions are continuous, and if pi is a non-standard probability measure on here, I mean, so yeah, you should disregard t theta. So I'll just say it in words. So basically, it says that if the parameter space is compact Hausdorff and the risk functions are continuous, then the non-standard Bayes risk of delta 0 with respect to the non-standard pi equals to the standard Bayes risk of delta 0 with respect to the pushdown up to an infinitesimal. So the second result says that suppose the risk functions are bounded, then the non-standard Bayes risk of delta 0 with respect to pi equals to the Bayes risk of delta 0 with respect to the internal pushdown up to an infinitesimal. So these two results connect non-standard prior, pushdown, and internal pushdown, and also allow us to derive the following two standard results from our main result. So recall that our main theorem is that a decision procedure is extended admissible if and only if it is non-standard Bayes. So these strong connections generate the following two purely standard results. So the first result says that if theta is compact Hausdorff and risk functions are continuous, then a decision procedure is extended admissible if and only if it is Bayes. The second result says that if the parameter space is measurable and risk functions are bounded, then a decision procedure is extended admissible if and only if it is finitely additive Bayes. Okay, so now I think I will give a conclusion of today's talk. So in this talk, I have defined a new notion of Bayes optimality known as non-standard Bayes optimality. And our main result shows that extended admissible is equivalent to non-standard Bayes optimality. And this result holds in any statistical decision problems under complete generality. And finally, we established two standard results using our main result in non-standard analysis. And this established how to connect, how to push down a non-standard theorem to a standard structure and obtain standard results. So this is the first step of our program of rebuild foundations of statistical decision theory using a non-standard analysis. So we also have some subsequent work on the existence of matching priors on compact space, and also some results on minimax theorem, which is similar in nature as the result presented in this talk, and also some more results on the stepwise Bayes procedures. And in particular, in that result, we give a very nice non-standard characterization of admissibility instead of extended admissibility. And we hope to finish that work soon. And I will be very happy to share all these works with the group once we have those manuscripts ready. Thank you very much for listening.
Thank you very much, Kevin. Snow, do we end the recording from here?